for this lecture, continuation nung sa power plant. Review lang, this is something na discuss na nung ChE 142, a heat engine. So if you will remember, these are machines that operate in a cycle to do a certain amount of net positive work as a result of heat transfer from a high temperature body to a low temperature body. And examples, we have steam power plant, Carnot engine, gas turbine, internal combustion engine, nuclear power plant, fossil fuel power plants. And this is the diagram of a heat engine. As you can see, ito yung heat engine itself. It extracts a certain amount of heat from a high temperature reservoir to produce a certain amount of net positive work. Then it dumps yung heat to a low temperature reservoir. So my question is, if you will remember sa ChE 142, possible ba to na mag-extract siya ng heat and then purely convert sa work? No, it goes against, okay, yung laws ng thermodynamics. So, hindi yan possible. Laging merong madadump ng heat sa cold temperature reservoir. So, yan. In a steam power plant, it's a large-scale heat engine wherein the working fluid is in steady state, pump through the cycle. So, gumagamit ng pump, boiler, turbine, and a condenser. So, yun yung four basic parts ng steam power plant. Pump, boiler, turbine, and condenser. And then, heat is transferred across a physical boundary. So, for example, we have a coal-fired power plant. Okay. So, sa power plant, sinasabi lang na ito yung basic na parts, but of course, may mga other parts, may accessory parts pa yan. Like ito yung complete package. Pero ang sinasabi ko, ito lang, itong part na to, this would be the heart of the power plant, which is composed of the turbine, condenser, pump, boiler. Okay? But of course, kailangan yung sa boiler, yung combustion gases niya, ilabas niya dito sa sa tower. And then, of course, merong generator din kasi from the turbine ko convert sa electrical energy. And yung sa condenser, kailangan niyang gumamit ng cooling tower para i-cool down and ma-recycle yung water back to the condenser. Pero ito yung basic part, ito yung heart ng power plant. And a Carnot engine, if you will remember, it's a heat engine operating in a completely reversible manner. And it operates between two reservoirs. All heat is absorbed and transferred towards the temperature of that reservoir, and all heat rejected is transferred at the constant temperature of the cold reservoir. Review na lang to kasi na-discuss nyo na to ng ChE 142. It consists of 4 steps. 2 reversible adiabatic and 2 reversible isothermal process. Okay. So, ano yung itsura ulit? Ito yung adiabatic. Okay. Ito, adiabatic na bringing the temperature to the temperature of the hot reservoir. And then, this is the isothermal absorption of heat from the hot reservoir. The next step is the adiabatic, bringing down the temperature to the temperature of the cold reservoir. And then, sa final step, yung isothermal absorption, release of heat to the low temperature or cold reservoir. And we that the efficiency of a Carnot cycle is calculated this way, diba? It's actually the work net over QH, but the work net is equal to QH minus QC, so substituting that into the equation, and ni absolute value signs kasi may sign conventions tayo for Q and W, which are pag Q is added to the system, di ba, positive. Pag Q is released from the system, negative. Work is done on the system, positive. Work is done by the system, negative. Please, pakitandaan yon. Ayan. And we can also express yung efficiency in terms of the absolute temperature. Remember, in the Carnot engine, the substance does not matter. So, hindi nagmamatter yung substance. Ano lang nagmamatter? Yung temperatures lang ng hot and cold reservoir. That's why, in the efficiency, wala ka makikitang substance dyan. Temperature lang ng hot and cold reservoir. This is the TS diagram of a Carnot cycle. So, in your y-axis, you have the T, okay, temperature, and in your x-axis, you have the entropy. So, gamit na gamit natin ang TS diagram dito sa production of power from heat. And this is your saturation curve. Okay, this is the saturated liquid line, yung nasa left. Then, saturated vapor line, yung nasa right. In the Carnot cycle, nandito lang siya sa loob ng saturated curve. So, yung fluid mo ay wet lang siya. Wet. It just cycles inside the saturated curve. Okay. So, from step 1 to 2, this is the isothermal. Kaya it happens at one temperature. Horizontal lang yung line. Isothermal absorption of heat. Okay. Step 2 to 3, this is the reversible adiabatic. So, pag sinabing reversible adiabatic, ano bang implication nun? Reversible na adiabatic pa. Ibig sabihin, delta S is 0. That's why vertical line lang siya kasi yung final mo, S3, is equal to S2. Kaya vertical line. Step 3 to 4 is also an isothermal horizontal line. Heat rejection to the cold reservoir. Step 4 to 1 is the reversible adiabatic. So, ganun ulit. Delta S is 0. S1 equal to S4. So, vertical line siya sa TS diagram. It happens at the same S. Kaya square lang siya. Square ang Carnot cycle. So, sa TS diagram. As a reversible cycle, it could serve as a standard of comparison for actual steam power plants. Diba, lagi ginagamit natin yung reversible process as the basis or reference, as it gives us the work max in this case. Ayan. The other type of cycle is the Rankine cycle. It's an alternative model and which serves as a standard for fossil fuel burning power plants. It is based on the Carnot cycle, but it fixed some practical difficulties. Ano ba yung mga practical difficulties pag ginamit natin yung Carnot cycle in actual power plants? Una-una, hindi talaga pwedeng, hindi possible yung Carnot cycle in actual power plants. Yung some reasons ay kasi yung turbines that take in saturated steam produce an exhaust with high liquid content, which cause severe erosion problems. Dito kasi sa diagram ni Carnot, this one is the boiler. Dito yung turbine. itong cycle na to. Ito yung condenser. Ito yung pump. Okay? Kasi ito yung expansion. So, this is the turbine. Boiler, di ba dyan nag-absorb ng heat. So, yung turbine na sa Carnot, nandito siya sa loob ng saturated vapor curve. So, ibig sabihin, nagtitake in siya ng saturated liquid pag-expand niya. And it causes some serious erosion problems sa turbine. Pangalawa, yung design ng pump na nagtitake in ng mixture ng liquid and vapor. As you can see here sa Carnot, yung pump, ito yan sa side na to. This is the pump side. Okay? Nasa loob din siya ng saturated vapor curve. Meaning, may device dapat na nagtitake in both ng saturated liquid tsaka saturated vapor. Which is, wala pa tayong ganong device sa siguro meron yung sa mga small scale, di ko pa sure, pero at least sa industrial scale, yung pumps natin is for liquids, compressor is for vapor. So, anong ginawa ni Rankine cycle? Instead of saturated vapor siya, pagpasok sa turbine, ginawa niya na may reheating, merong superheating pala. May superheating, symbol, ang representation sa diagram, superheating, bumalik siya sa boiler, lumabas ulit. Para superheated siya pagpasok ng turbine, hindi lang saturated vapor pagpasok ng turbine. And then, isa pa, paglabas ng condenser ay lalabas siya ng saturated liquid region. Lalabas siya para sa subcooled siya. Para yung pump, ang i-handle lang niya, subcooled at saka purely saturated liquid. Yan. So, ano itsura sa TS diagram? Ito yun. Una, may superheating. Okay? May superheating, lumabas siya ng saturated region. So, this is the superheated region na sa TS diagram. So, pagpasok niya sa turbine, superheated siya. Then, dito naman, paglabas niya ng condenser, kasi kanina nandito yung sa Carnot, sinagad niya hanggang sa lumabas siya sa saturated liquid, lumabas siya sa subcooled region para yung pump, ang i-handle lang niya ay saturated liquid at saka subcooled na subs na liquid. Okay. So, na-solve na yung mga problems ng Carnot cycle. So, from step 1 to 2, by the way, itong curve na to, ito, yan, that's an isobar. Okay? And this one, that's another isobar. So, yung step 1 to 2, it's constant pressure heating process in the boiler. Na may tatlong section, yung heating of subcooled liquid to its saturation temperature, ito yon. And then, step 2, vaporization of at constant pressure and constant temperature, ito yon, the horizontal line. So, constant temperature yan kasi horizontal line. And, diba, sa TS diagram, ito yung y-axis. Tama. Tapos, at the same time, isobar kasi yan. And remember, if saturated yung substance natin, phase change happens at a constant pressure and constant temperature. Kaya, straight line, horizontal line, sa loob ng saturated curve. Wala siyang choice. Hindi possible ito. Hindi pwede mag-slant yan. Mali. Lagi pag nasa loob ka ng saturated curve, straight line ka lang sa TS diagram. Kasi, it happens at one temperature, phase change, and at one pressure. Kaya yung isobar natin, pagdating sa loob ng saturated curve, nagiging straight horizontal line siya. The next is superheating of the vapor to a temperature above its T saturation. So, ito yung part na yon, yun yung superheating. Lumabas na siya ng saturated curve. And then, next is step 2 to 3, reversible adiabatic expansion. So, ito naman yon. Ito yon sa turbine. Mag-expand siya. Okay? Next is isothermal and isobaric cooling in a condenser to produce a saturated liquid. So, ito yon yung condenser to produce a saturated liquid. Next is reversible adiabatic pumping of the saturated liquid to produce a subcooled liquid. So, ito yon yung maliit na part na yan. So, ang shape niyan nung ating cycle ay from yung Carnot na square, naging ganyan na yung shape. Yan. Now, the power plants can be built to operate on a cycle that departs from the Rankine cycle solely because of the irreversibilities. So, yung kanina kasi, yung Rankine cycle natin, ano mapapansin nyo? Meron pa rin siyang irreversible, meron siyang line na vertical, okay, yung sa S. Pag vertical line kasi, ibig sabihin delta is 0, which is impossible sa real life, no? So, lagi dapat medyo paslant siya to the right. Okay? Ito rin, straight to kanina. So, ito, straight dapat to. So, dalawang parts yung straight line siya na impossible kasi delta is 0. Yung sa turbine, pag-expand, at saka yung sa pumping. Ito, delta is 0. So, dapat ang shape niya in real life maging slant, a bit of a slant, no, pag ganon. So, pag ganon yung turbine, sa turbine, and then yung sa pump pag ganon. Hindi, lagi tayo towards, okay, since clockwise yung cycle natin, lagi tayo towards a higher entropy. Diba? This is the S, this is T. So, dito rin dapat laging papunta sa higher entropy. Okay? Nakuha ba? So, yan yung direction. Ito yung direction. Lines 2 to 3 and 4 are no longer vertical but tend in direction of increase in entropy. Yan nga yun, yung sinasabi ko. The turbine exhaust is normally still wet, but as long as the moisture content is less than 10%, erosion problems are not serious. So, pagdating dito, okay, siya, pumasok siya ng saturated curve, meaning wet pa rin siya. Pero as long as 10% or less yung moisture content, okay lang yon. Kasi yung sa Carnot, napaka-wet niya dahil dito siya sa part na yon. Pero dito kasi, nag-superheat, ayan, lumapit siya sa saturated vapor curve. Pag mas malapit ka sa saturated vapor curve, ibig sabihin, mas konti yung moisture mo, mas madami yung vapor mo, diba? So, ibig sabihin, mas advantageous tong sa Rankine cycle na in such a way na pag-expand ng gas sa turbine, konti pa rin yung moisture niya compared to Carnot cycle. And lastly, may slight subcooling of condensate in the condenser may occur, but the effect is inconsequential. So, may slight subcooling daw kasi minsan lalabas siya, condenser pa rin, pero nasa labas na siya ng saturated liquid curve. Okay? Pero wala masyadong effect yan sa condenser. If we do an energy balance, okay, in the boiler and condenser, assuming delta PE, delta KE is 0, wala tayong moving parts, and then assuming na, ayan, so sa boiler and condenser, ito yung working equation natin. Q is just the delta H times mass of flowing stream. Now, if we do an energy balance in the turbine, wala din tayong delta PE and KE, Q is 0. This is our working equation sa turbine, which is solve na natin ito doon sa previous steady state devices, diba? Yan yung working equation for the turbine. And then sa pump, na-solve na rin natin to sa previous lecture, diba? Ito rin yung working equation natin sa pump, pero nga, since pwede natin i-utilize yung fundamental property relation kasi para ma-solve, kasi wala tayong data ng subcooled liquid. If we do that, basically, yung delta HS natin is just V delta P. Okay, so bakit nga ulit? Kasi, when we assume na isentropic, masi-zero out to. So, pag inano mo siya, in-integrate mo siya, you are left with VdP, integral of that. Pero since we can assume na V is not a function of dP, ang integral lang niyan ay V delta P. Yan. Okay, but that's assuming na isentropic yung pumping. Kaya, kailangan mo ng efficiency para ma-solve yung actual pump work. And we can now write the efficiency of the power plant as work over QH. Okay. So, yung work dito, makukuha mo siya dun sa part ng turbine, sa expansion. So, yan yung sa expansion. Ito naman yung sa part ng boiler, yung pag-absorb niya ng heat. Okay? Okay, so it depends sa label mo, hindi necessarily H2, H1, yan, basta kung anong nilabel mo dito, pwedeng A, B, C, D, ganon, yun yung, halimbawa, nilabel ko dito, A, B, C, D, E. So, yung work ko is HD minus HC. Tapos, yung absorb na heat ko ay HC minus HA. Yun. So, not necessarily gagamitin mo. Basta yung work dyan is yung sa turbine, ito sa boiler. Okay? So, yung next na video, we will answer this sample problem.